Okay, then our next speaker is Gábor Csányi. Gábor received his PhD in 2001 from MIT, and then moved back to Cambridge, where he studied before also, and worked there as a researcher and as a lecturer for quite some time until he became professor in 2016, also there. He's been famous, I guess, for working a lot on molecular representations for quite some time, and then most well known, I think, for the quite popular family of maze models and architecture. His work has been honored by several awards, including the Best Award from the Alexander von Humboldt Foundation, and he has recently been elected Fellow of the Royal Society. And after many years in Cambridge, he is now relocating to Germany and to the prestigious position of director of the Max Planck Institute for Polymer Research in Mainz. So, Gábor, we welcome you, and I'm looking forward to your talk.
Thank you. Nice to be back here in this lecture room. I spent many exciting hours at the tea workshop a couple of years ago now, I guess. A little whirlwind tour of activities in force fields. I'm always tempted to talk about history, as you could tell with Klaus Robert as well. The older you get, the more important the past becomes. And then you exit, and then the past moves on to the next generation. But I'll try to split some time. So computational cost is what this field is all about, right? If you want to better understand the world at the lowest length scales, you go for the accuracy, you improve your electronic structure methods, and maybe even at lower length scales. But if you actually want to compute something real that has a direct relevance and touches experimental work in many different facets of it, then you need to be able to compute fast, compute large systems. Lots of people will know this, but just to get home the timescales involved, a low-level DFT calculation still takes about an hour on a compute node. Take these with on the log scale within a factor of 2, but that's what you can do with explicit electrons. And of course, you always say it's cubically scaling. It isn't necessarily. There are linear scaling methods. They have lots of limitations. And so in this regime of 100 atoms, where lots and lots of calculations can be done, the scaling is certainly not very different from cubic. But so if you wanted to do 1,000 atoms and you stuck to the well-established cubic scaling methods, it would take you 1,000 hours, and now you can do that, and sometimes people do that. But if you want to do a much better DFT calculation, a hybrid calculation, you incur prefactors, you incur reverse scaling, and so 1,000 atom calculation is 200,000 hours. Maybe you can do one if you can convince somebody to give you the 200,000 hours. It's not clear how useful that will be. What can you accomplish by doing one calculation of 1,000 atoms? If you move over to, this is for materials examples, if you go over to molecules and you want to do a couple cluster calculation, it scales very steeply. Again, there are lower scaling versions. The communities at the forefront are debating the applicability and accuracy of those. But if you stuck with the canonical couple cluster, it would cost you 10 million hours, and really it's quite questionable why you would spend to do that. And so DFT is what people do. Low-level DFT is what most people do. If you just look at the counts, some of these, this graph is five years old. This one is only 1 year old. With blue, I indicated DFT calculations. This is academic usage of national facilities. And you can see that in the UK, about 40%, if you add up all the blue bars, about 40% of time was spent in the last, in a couple of years ago, on DFT calculations, mostly NT. In the US, 30% of this particular large machine was spent on doing DFT calculations. That's what the community is doing. And so if we could, when this field of ML force fields, if we can manage to speed that up significantly by many, many orders of magnitude, then we're really having an impact. Because all these people who are doing these calculations and all the people who are doing these calculations are going to take notice and do something different. And this is, again, for the younger members in the audience, these many, many zeros is what you want to see when you enter a research field, when you want to say, I'm going to make a difference, and if I'm successful, all these zeros I can cut. Okay? If you're going to embark on a PhD and say, if that PhD is super successful and you're going to make a difference of a factor of 2 to a calculation, you will publish a nice paper, but your career is not going to take off because of that. So I encourage you to zoom out a little bit from your individual projects and consider why has this field been so successful, and the fact that this could be predicted 20 years ago, because these numbers, because of the steep scaling of it, haven't changed very much over the decades. And this is what the two large conferences of materials on the left, Psyche and Molecules, the VATOC, World Association of Theoretical and Organic Chemistry, which is mostly computational chemistry basically. These are the programs, and I highlighted in red the talks in which machine learned force fields or machine learned intraatomic potentials were in the title. So these talks were about, they were not using ML force fields, they were talks about how to make them. And so it's about 20% of the talks were about that. And of course that's going to go away. In 5 years' time, nobody will talk about how to make ML force fields on this scale, because everybody will be using them. It will be sort of old news. And so if you think about what happened in the last 15 years, we've applied the ML technology to this problem. Errors have come down. We've explored model architectures. What limits the accuracy? There's lots and lots of talk about errors, and the numbers are getting smaller, but it's helpful to think about what is this limit. So model architecture can certainly limit it, and there are situations and cases where that needs to be changed, and that's interesting for a lot of us who think about that. There are hyperparameters in the model architectures, like the range of an interaction or the resolution with which you describe a geometry that can limit, and that you can change at will. And of course, you move up and down on this Pareto front that many of the previous speakers have talked about, and that is a very, very useful thing to do. There are people in this room who make models that are extremely fast, and there are people who make models that are extremely accurate, and they both have legitimacy, perhaps for slightly different applications. One limitation of the error, certainly when you compare to experiment, and when you compare to very high-level electronic structure, is the electronic structure approximation itself. And I think that is a very interesting thing to see in this field, that as these surrogates become very good, they highlight limitations of electronic structure, and they spur on developments of electronic structure, because now it's worth it. Now it's worth creating a new electronic structure method that is perhaps quite expensive, but can serve as training data, and therefore its cost can be amortized. So let me give you the one slide worth of deep history of the descriptors, because I can use that to throw up some equations which then connect through the years. So back in 2010, 2013, we were working with the SOAP descriptor, and its architecture is kind of visible in what we're doing later on. So we start with expanding the atomic density, rho I. It's a sum over the neighborhood. So J is a neighbor of atom I, and we put a Gaussian on each atom. Later on, these Gaussians, you can actually make them delta functions, it doesn't matter, but originally we certainly used finite Gaussians here. And you expand that density into YLMs. And this is the famous density trick that was mentioned before already here. So it becomes linear scaling in the number of neighbors, because there's only a simple sum over the number of neighbors here, and the number of neighbors doesn't appear anywhere else. If you take that limit of sigma go to 0, so that's just delta functions of the neighbors, then there's an explicit formula for the coefficients of this YLM radial expansion. And then, after you've done that, you can then create invariants. And these this product of the coefficients here with a complex conjugate here creates you what we used to call a SOAP vector, with 3 indices for each atom I, and N prime and L, and it's just the first primitive version of these invariants with which you can make, based on which you can then make a potential. And then the big change, which many of us have sort of pivoted to, came in 2019 when Ralph Draughts entered the field. It was uniquely positioned from his previous works, previous understanding, in uniting lots and lots of different ways of doing essentially what SOAP did. And he introduced the ACE formalism, which of course was mentioned before by the beginning in this talk. But look at how these things are very much ACE is a generalization of the original SOAP interaction. So here the same basis function, radials and YLMs, now explicitly with the atomic element number Z, and I'm changing notation because I'm just keeping the notation of the original papers in each case. But this sum over J of the expansion coefficients is exactly matching what SOAP did here, but now more generally these phi's, the radial function can be N dependent and L dependent and so on. So there's much more systematic expansion here. The next, we make the product, and here we just did a pairwise product, but Ralph realized that this is general and one can make an arbitrary number of products of these coefficients up to, again, truncated, just like you truncate N and L, and then you can truncate this product too, but in principle you can make arbitrary number of products of these coefficients. Nu is the truncation here, and you get this atomic basis here, tensor with lots and lots of tensorial indices. And then the second key realization of Ralph is that you can generate invariants. And the same, what looked very simple here with the coefficient of just 1, so you just need to add up these C dagger C here. When you have a general tensor product, you need non-unit coefficients, and these Clebsch-Gordon coefficients called C here, capital C, is what creates the invariants. And there's a lot of representation theory in what they are. They are in the textbook. There's a formula that generates them. And Christoph Ordner and Ralph worked hard to formalize this, make this B basis, the ACE basis, orthogonal linear complete basis for describing geometry. So then that was very good, and ACE was much better than things based on SOAP, but one could do better. And in fact, I learned that one needs to do better from Robert and Alex here, and also Boris Kozinski and Stefan, because you guys were working on molecules, and in fact what happened was that with materials we couldn't do better than ACE, simply because we reached, and we knew that because we reached the limitations of the electronic structure methods. So electronic structure, you could do DFT to a level of convergence, and we had ACE models that had the same accuracy as the data error in materials. So why do anything different? But you could never do better. But for molecules, that was far from the case. The electronic structure methods are much more accurate for molecules. I don't mean closer to reality. I mean, they could be converged to a much better level of numerical accuracy. And SOAP models and ACE models were nowhere near that accuracy. And so there was clearly models that could do much better, and models made by Lear were doing much better for molecules. So ACE was missing something. And then for me personally, I don't know how it happened for others, but for me personally, the breakthrough idea came from Boris, who was building on message passing ideas before. So what is message passing here? It's basically, if you think of the ACE model, a local descriptor model that has an atom at the center and integrates information from a finite neighborhood from up to some cutoff R. If you want to make the model more accurate, ACE is in principle a complete basis, so you make it more accurate by increasing the receptive field. And this is what happens. These arrows indicate the flow of information, flow of geometric information to the central atom, to these B basis functions, and you can increase the basis set and get much, much more data. But it turns out that for any given data set, for any given set of hyperparameters, this runs out of steam very quickly in practice. You don't get much more accuracy when you take R-cut beyond 6 angstroms. And what message passing does instead is it introduces an information bottleneck, a concept that's very well explored and well known in machine learning, so that the information I get from these faraway atoms don't come directly, they come via an intermediate atom. So that's the message, so that each atom integrates information from some smaller neighborhood, and then that information gets compressed and passed on to the next one. So in our formulation, that became the MACE method. Already, of course, that message passing was introduced into force fields using the Schnapp model, using NeQuip, and so on. In our hands, it became MACE because we put that together with ACE. So the equations get slightly more complicated, but there's still the correspondence. So you have a pair basis of radial and YLM. So here's the radial, here's the YLM. The other letters are needed in a moment because we do message passing. But then the sum over J of this phi is the same as for ACE. The product of normal A's to become bold A, that's when you get the many-body density trick, is also the same. And the construction of the invariance and equivariance now, the scalars, vectors, tensors that rotate in the appropriate way, is again exactly the same as it was done with Ace. And the difference comes that you don't just stop here, but then you go back and do it again. So you generate these features H, which initially are just linear combination of the B's, you go back and you re-expand. So these H's, that's where the compression happens. And you come back and do it once more. And when you do it to the Ace rather than to just invariance, as in earlier models, of course, NeQuip was the first one to do this, but it only did it only involved pairs, so it didn't have this kind of product here. When you do it to the H base, it becomes very efficient. So you only need to do this twice. Only 2 iterations are needed to get a very, very good accuracy. And in fact, much more recently, there is this proof that the MACE construction, so multi-body using this ACE product here and then iterating twice, gives you this long sought after unique geometric representation from which you can reconstruct the original geometry of any system up to rotations and permutations. And the Taylor-Rose constructions is a constructive proof. It actually gives you an algorithm for reconstruction. And to my mind, that is what explains the accuracy and efficiency of these multi-body message passing models. So here's a graphical history of ML force fields going back even further than this 10-15 years. So we can, before the seminal work of Baylor and Parnello in 2007, you had low-dimensional fits. Yeah, you know how to run simple neural networks, and you can fit complicated functions in low dimensions easily. But of course, there's limited accuracy and expressivity. It doesn't extrapolate. And then with the high-dimensional neural networks and representations, so that's the atom-centered representations that Baylor and Parnell introduced, you could now go out and do many, many different local minima as long as you had the data, but there's still not very good extrapolation. And the extrapolation came, as people now know, from the expressivity of equivariant networks and message passing. So this is where you have these foundation models that trained on small amounts of data, especially this is true for materials, much smaller than generally what you want to study, and it gives a reasonable behavior elsewhere, and you can fine tune if you want. I would say that we still don't really fully understand why it can be, why it extrapolates reasonably. Why is there MD stability of material models? That is, I think there are intuitions, but not mathematically solid answers here. So how has that changed life in materials modeling? Well, before that, we had iterative workflows, active learning. I'm not going to go through the details, but imagine complex workflows where you want to create a bespoke potential, in this case for a catalytic system, and you have this UML diagram of what you need to do, how you collect DFT data for a specific system, lots and lots of design choices in how you build up an active learning workflow and build up a database and a fit. and you build a model for each system, the workflow is expensive, and it requires, and this is the real killer, it requires domain expertise in order to set up, run, and evaluate. It's not really scalable. So the question was, I guess 3-4 years ago, even more, if you look at this day, 6 years ago, is can you build a general force field for materials? Materials and molecules separate here a little bit, because for molecules, empirical force fields were general, they were not that accurate, and they took, as explained before, they took a lot of expertise to make really accurate for a new system, but they generally applied for the organic molecular systems. But for materials, there were no general force fields that had any reasonable, that had a very wide applicability. There were attempts, but they were not very good. And so the question was, can you make a force field that is pretty reasonable for every material? And nobody thought that that was a viable thing. Certainly none of my community who worked on SOAP and ACE and MACE. There were people who were thinking about that. Xu Pingong springs to mind, who curated, not surprisingly, he was the person who curated the materials project database. So he had the data, he had the view of the data, and started creating models, MagNet in 2018 and M3GNet in 2022, which focused on materials discovery. So you fit them on these small inorganic compounds. Here's a little movie of all known inorganic materials, about 150,000 that have been made in the lab or close to those material structures, maybe 50,000 in the lab, another 100,000 explored with DFT around those materials. And that is what's in the materials project, or what was in the materials project at the time, and covering 89 elements. So really most of the non-radioactive elements. Relatively small displacements for equilibrium, not all at equilibrium, but close by. And these models were used to study small inorganic crystals, right? So doing materials discovery. Can you create a new material? And that's what Xu Pingong was really after. And this is the state of the materials project benchmark at the time. So this is November 2023, and with a little bit of help from my students, the people who made the benchmark, János Ribesel and co-workers, made MACE the top of the leaderboard quite easily, without sort of a lot of extra work, and that kicked off quite a spur. In a few months, there was something much better. In a huge number of parameters from Google. In a few months more, just a whole slew of models started coming in and hitting that, and really pushing that boundary, pushing that envelope. This benchmark, there's lots and lots of columns. They're all very, very correlated. It's all about measuring the energy accuracy of a couple of unknown structures, nothing else. And so the community started scrutinizing this benchmark aggressively, and it turned out that energies were very good, forces were not very good with these models. So this kappa column was introduced around about 2 years ago, and you can see that this is the first column that totally doesn't correlate with anything else, because it measures force accuracy rather than energy accuracy. And it turned out that if you look at the numbers, look, this MACE model that is now far, far down the list is now the best in forces, because some of these people were just really trying to optimize this energy benchmark. Those models didn't really, apart from Matheson, which simply just didn't run the benchmark. Here, Matheson is very good, but all these others, this is equivariant transformers, and ORB is a bizarre model. 7net is NECVIV, which is also very good. It's close to the architecture of MACE. All these transformer-based models here were completely unusable as force fields. They were so unsmooth that the forces were off the chart. This then got fixed as people have seen the utility of benchmarks. And now, of course, the MPA model is still very good, but this doesn't last very long. You see the most recent versions in the previous talks. There are now dozens and dozens of models that do extremely well, including on forces. But this still doesn't answer the question of what are these models really universal? What happens when you try to do something completely different with them? not measure the energy of small inorganic unit cells, even if they are unknown. And so this is where, to my mind, the surprise came. So this is a structure which I asked a student of mine to run because there was an end of grant meeting in Brussels. I had 5 minutes to give a talk about why we couldn't run a simulation like this, why we couldn't make a force field for a battery electrolyte interface. So this is an anode and this is an electrolyte, because every previous attempt of this just failed, exploded. We couldn't control the fits. So I wanted to show one of those explosions, so I gave this model that was fitted to small inorganic crystals, at least it knew about all the elements, and asked my student to run an MD to show the explosion, to explain why this problem is hard. And then he came back a day later saying, well, sorry boss, it didn't explode. And I said, what do you mean it didn't explode? Every model explodes when you try to fit such a complex system, every purpose-built model. And so he said, well, I don't know, here it is. So that was strange. We tried to hunt for some trivial bugs, but we couldn't. This was the first time that we saw a model widely extrapolate and solve a problem, a very artificial problem, stable MD. Never mind whether it does the real battery science or not. Does it simply keep the structure together? And then very shortly after that, we tried it on other systems because it's so surprising. And batteries were okay, and perovskites were okay, and aqueous interfaces, and amorphous carbon, and polymerization of sulfur, and everything we tried it on. At room temperature, moderate system size, ND was stable. And that was shocking, because none of these systems were in the training set at all, like not even near. You could burn hydrogen with this model and get water, hydrogen, oxygen, put it together, get water. Inside it, there was ozone, there was H2O2, all the things that you'd expect to see when you burn water. And these were not simulations with which you now go and solve a scientific problem, because they weren't that accurate. But for the first time, we saw this dramatic extrapolation, which was methodologically something very new. The models were reasonably fast, so this happened without giving up the huge gain over DFT. So this is the very original model, the MP0 model, and you can see that we reach this number of atoms here. This is log of nanoseconds. So this dashed line is 1 nanoseconds per day, and you could get 10 nanoseconds on very small systems, and up to on GPUs and CPUs if you do weak scaling. So add the number of, increase the number of CPUs or increase the number of GPUs as you add more atoms. You could sustain a nanosecond per day to a couple of tens of thousands of atoms, and it's linear scaling. So this is the one. Of course, since then, this huge amount of work has been done on kernels and special coding for GPUs, and people can now do orders of magnitude better than this, or more atoms rather, and keep the few nanoseconds per day, which is sort of where you want to be really if you were going to replace DFT. Message passing scales. So let's talk about failures. Let's talk about what these models can't do. And one of the things that's really difficult is changing density. And you can see that, actually, this is a dramatic example, but density is super hard, because these radial basis sets, that is where a lot of the parameters are, as you change the density, they become inappropriate. So this is a graph of the MP0 model, the first this universal foundation model that has been showing this amazing extrapolation. And this is what it does when you take different structures of arsenic and you compress them. What you expect is that the energy should just go up. Instead, you get this mess. And anybody who's ever fitted ML potentials, no matter what kind, whether purpose-built or, will know this very well. This sort of crazy stuff when you get to very small distances. And look at the data density. So this is the histogram of arsenic distances in the training set, right? It starts at 2.4 and goes up. So there's nothing in the training set below 2.4. The extrapolation that I was so proud of, that I was telling you, oh, this model extrapolates everywhere, completely fails here. And this is a general case that in this direction of compression, the model doesn't extrapolate at all. it extrapolates in chemical space, but not in radial space. So we tried lots and lots of things to fix it as a practical problem. Tried increasing the model size, it didn't really help. We tried lots of tricks, and in the end, putting more physics into the model. So fitting the atomization energy rather than the total energy. So putting the isolated atom, fixing that at 0, putting in some close approach repulsion, because I don't really care about the electronic structure here. Look at the EV scale. I just want it to be repulsive. I don't really mind how. I don't want the detail. Adjusting the radial sensitivity, turning down the many, many billions of neural network parameters that allow these functions to be so oscillatory. We want to remove them. And then other tricks that are common in machine learning, layer normalization and so on, these eventually get you to what you want. So isolated atom reference energies are like this, adding ZBL splines. There are still a few kinks, but it's not a mess like that. And then you put in a distance transform, and that turns down the sensitivity of the network at low distances, and then density normalization at the end, so that you don't have a situation where the number of neighbors, which changes by 2 orders of magnitude, is really throwing off the neural network here, and that gives you that decent potential energy surface. So this is one of those examples where you throw in millions of parameters, you throw in the data, you've swallowed the bitter lesson, just let the data do everything, and then there are failure modes. And in this case, we fix the failure modes by putting in all the physics. You can fix the failure mode by putting in more data. So that's what Microsoft did with Mattersight. You put in the high density DFTs, but you have to work hard because DFT with standard pseudopotentials doesn't converge when you go to very small distances and so on. And do you actually care? You now maybe wasting 90% of your data generation capacity in a regime that you don't actually care about just because you want stability. So I think this is one of those cases where putting in the physics just made more sense. So the new game is really fine-tuning. Instead of purpose-built potentials, you say, let's take these foundation models. We call them foundations, controversial term. We call them foundations because they're not universal. They are foundations to be built upon. You need to fine-tune them. If you had a model that does DFT with arbitrary accuracy forever, fine, you can call it a universal model. But that was the original foundations. People criticize it because it doesn't, it's not an LLM and it doesn't tell you what the next drug should be when you ask it in English, which is what they expect from a foundation model. But it's foundational in the sense that you can do different kind of chemistries, right? Lots of different materials, lots of different molecules you can do without and get the stable MD. So what you do with fine tuning is that you take the model, you run your system, and then you collect data and you fine tune, and you get a model for that new data set that is very accurate. Now there's a lot of different ways of doing that. You can just do it naively. You take the parameters, you put the new data, and you get new parameters which match the data. You can do multi-head fine tuning, where you take some of the model trains on the old data, another head on the new data, they work together. You can freeze some layers where you don't allow them to change and only allow the new layers to change. Or you can do low-rank approximations and so on. There's a recent preprint coming soon. I think it's on the archive now, where this has been explored. And there are some couple of interesting lessons drawn from here. It doesn't take much data to fine-tune. So this is all the applications in the MP0 paper, but just 100 new configurations for each application gives you force RMSE drops of an order of magnitude, typically, compared to the original model. And of course, concurrently with that, you get the accuracy that you want for physical observables. So here's just, again, a very quick view of that. This is the catalytic reaction that we studied before. And the original model, the DFT is sort of purple here. The original model is orange. And you can see that although peaks and troughs are in the right place often, there are big discrepancies. There are big changes in absorption energy. And just put 5 new configurations for each of these reactions, and you get the pink, the sort of light blue line goes and matches the barriers much better. Not always perfectly, but much better than without fine-tuning. It's good enough for this application. So here's a sort of family tree. This is how I think about the history. So there's lots and lots of methods here that are colored according to representation. So how do they represent the atoms? Here we've heard about GDML and SGDML before. They are global models. We have the atom-centered symmetry functions of Europe-Baylor. We have the Schnedt model, and so on, that then I've drawn and carefully considered these different relationships. Here's my own trajectory of SOAP, ACE, and MACE. These are density trick models, density tricks with spherical harmonics. Alex Shapir should get a mention, who studied very early on, an applied mathematician, and studied both in Russia and the US. And he did the same thing with Cartesian tensors, essentially equivalently to what Ralph Krauss did with ACE, with spherical tensors. And lots of these have now kind of merged into these foundational emblems. So here we collected lots of models which are on the materials discovery benchmark. They all solve these problems of locality, the receptive field, smoothness. They all have many-body interactions. They all do chemical embedding, and almost all of them solve the rotational symmetry in some way, either analytically or by data augmentation. And we start to look for scaling laws to see which direction should we put more data in, should we put more parameters, should we make the models more complex. The picture is a little bit mixed. So here's the materials discovery score. Here's the amount of data, and models that are just retrained on more data, but same architecture, are linked with a line. And you see that the lines go up and right. Okay, so if you put more data in, there's a better score. But otherwise, and equivariant GNNs perform very well. Transformers sometimes perform well, sometimes they don't. So this is a transformer model, and this is a transformer model, very large. More data is always better, and more parameters are not necessarily better. So there are very small models here. That's the size of the symbol. And the architecture limitations are still present. You can still make very big gains by putting in new architectures. You can dig deeper. So here's an analysis of relaxations of new hypothetical materials, and ranked according to to what extent do they keep the symmetry of the DFT relaxed structure. This is a very, very sensitive observable, and it tells you a little bit about how smooth the potential energy surface is and how symmetric. And you see a completely different ranking from the standard ranking, right? So this is the RMSD here is close to the standard ranking, because it correlates with the standard ranking very well, but this is the ranking of how much you keep the symmetry. And what are the models that are at the top here? So M3GNet, MACE NP0, the very original, now completely outdated 3-year-old model. GRACE is up here, lots of different versions, TACE, another MACE, another GRACE, and so on. So models that have put in lots of physics, lots of very carefully controlled symmetries and smoothness, do extremely well on such a task. You can dig into the data in other ways. Here's a very surprising plot for most people. This is the OMAT data set, the 100 million data set that most of these models draw their breadth from. And this is the sum of the forces, which should be zero. These are plane wave calculations, so really it can be very, very small. On the NBT generated subset of it, and just look at, these are milli EV per atom. So you have, this is 1 EV per atom. We have a substantial tail of data error where the sum of the forces is EV per angstrom size. So this part of the data is really, really garbage. And that is also, and it's of course also in the testing data. So this limits the observed accuracy tremendously. Cleaning some of these big data sets, I think, is going to lead to a lot of lot of progress.
Using QCML.
Using?
QCML. It's not so much coverage.
Yeah, I mean, this is the material. You're standing up. give me the number of minutes. -1, -2?
It would be 5, but
5, okay, I can do 5. So multi-head cross-learning is another approach where how do we bring materials and molecules together? Everything is separate. I focused my talk on materials because that was the right thing to do here, the right balance. But of course, materials and molecules, currently, most people have separate models for it because that's how you get the best model for that domain. But there are interesting questions where you need materials and molecules. Catalysis is one, MOFs are another, and there are applications where you really want the best of both. And that's hard because even the electronic structure, appropriate electronic structure is different for those different domains. So our attempt at this is a multi-head model where we put in different data sets for materials and molecules together and use it with different heads. And that does very well. So if you then test it on materials and molecules, it is better than competing models, even ones which have had lots and lots of different data sets in it. This is this is at this point more art than methodological science, right? How you take compromise between incompatible DFTs and so on. I want to sort of close by pointing out the need for better tests. So lots and lots of development in the last 10 years was spurred on by just getting the RMSEs lower, getting better energies, getting better forces. Lots of people can do that now. What's more important now is how you extrapolate, how you do with MD, how you get observables. So we're building a performance and extrapolation guide. It's not a benchmark because the point is not to show which model is best forever, but allow the user to change the weights of the different tests. Those are these numbers here. You can pick the weight of the different tests and make any model come out top if you want, if that's what's important for you. The reason this is, you can actually see this thing online if you search for it. We haven't released it formally yet because we are ironing out some user interface issues which need to be ironed out. But I think a lot of the progress is going to now come from very, very wide benchmarking. If we can all, and I hope we can, all agree on what are useful benchmarks. So I always speak more slowly than I think, so I'm going to skip long-range models. We've heard about them before. Maybe I'll just do the summary slide. So we have a couple of recent preprints. I won't go into the detail, but one of them is about what happens when you don't use long-range models for material simulation, like an electrode and water, and we see false metallization. So we see these configurations generated by short-range models which have these potentials, delta V, inside the water that are huge, electrostatic potentials. You get 10 eV difference between different parts of the water. Essentially, this water is metallic. And the other thing you get with these short-range models, which is the black and the red here, is as you increase the system size, you get very, very slow relaxation. These structures have huge oriented dipole moments, they have these large potential differences, and they relax extremely slowly. Whereas a long-range model, any kind of long-range model, will keep the relaxation fast. The second paper is on designing long-range models, energy functionals, and fixed-point iterative methods. DFT does that formally. Classical models do that. You can have these models of QEQ, charge equilibration here, and simply polarizable dipole force fields over here, and we can do the same thing with ML. Describe energy models where we optimize charge to lower the energy, or fixed point models where we get the charge from potential and iterate. I won't go into the detail. Based on the second type, we create the Maze Polar 1 model, which includes a 1 over R due to the fixed point iteration of the Poisson solve. You do it twice, and you get a model trained on the OMO dataset, the largest molecular dataset currently there. It has problems. There are problems with its dispersion and so on, but we get a very, very good organic model. Let me skip the detail. I want to close with a plea for data here. This is the sizes of the data sets that we've been working with, more or less. PTRJ, SPICE2, Alexandria, OMAT. The QCD data set is about 35 million as well. Look at the largest one, $60 million to generate it, 6 petabytes of data. Where is the next one going to come from? This was generated by Faircap. If you want lots and lots of coupled cluster molecular data at a very, very high level of convergence, if you want materials with defects and external fields, where is that going to come from? I'm not sure. What I try to advocate is that the community should come together. Science has had fantastic results from everybody coming together to generate common assets. Particle accelerators spring to mind, space telescopes. You don't have competing space telescopes, and the PDB, of course. So I think what's needed is to argue, to compromise, to come to a common agreement on what a new data set should be in the different directions, and create a roadmap, and then let the contributions roll in on a voluntary basis. So hopefully you'll hear more about that in the coming months and years. Okay, thank you.
Thank you very much, Gábor. Yeah, let's have a couple of questions here. Alex.
So, Gábor, I mean, do you have any concrete ideas on what to do for materials? And for molecules, it's pretty clear.
Yeah, for molecules, it's more clear. I think for materials, we have a very long list. I think the external fields, and if you look at material data sets, almost all, and the ones that aren't have special problems, they are 3D periodic. And small 3D, that's how you get the variety. But the problem is that severely limits the extent to which you probe response functions, electrostatic response functions, because you're confined to a small cell in which the potential is periodic. You don't yank on the electrons enough. So I think that's the biggest limitation. We need slabs and electric fields. There are data sets like that, but they have severe geometric
What
problems.
about level of theory, right? I mean,
that's a whole. So one big problem is how you unite the levels of theory. If I want materials and molecules, there is no current DFT method out there that can predict reliably the absorption energy of molecules on material surfaces that works for metals and for oxides. And that's this is what I mentioned at the beginning, that because we now look for these universal methods and we don't mind the cost. Give me a method that's 100 times the cost of DFT. We will run it. And I think now the electronic structure community is reinvigorated by this huge demand. And something's going to come out of that. And when it does, we will need to use it to generate the data. And defects is the other, right? So defects, which need larger systems, they need supercells. How many do we need? 1 million times more structures than before? I'm not sure. I think there is extrapolation. I think there is, just like the materials project's chemical variety led to universal models, I think as long as we break the periodic symmetry in some ways, in important ways, I think we will give a big step. These are the two big directions. But you're right, the electronic structure problem is out there. There are some questions on the chat.
Yeah. So there are a few here. So one question from Chin to Das. During active learning, structures from the excluded part of a trajectory should they be added to the training set or not? Because including those will change the generalizability of the model on the training data set. On the other hand, including those can also make the model aware of those high energy configurations.
So I think this really depends on what your ultimate goal is, right? If you're in a project and you want a working potential in a couple of weeks, you do active learning, you add whatever you find to it, and it will be a much better potential for the range of structures that you're studying. And it can lose its generalizability and so on, although the fine-tuning paper the preprint that I mentioned also looks at this. There are tricks you can do in fine-tuning that make it much less prone to losing accuracy. But that's not how I would like to build a foundation model. I think this is the MatterSim approach from Microsoft. It's a good potential, actually. It's a very solid piece of work. I don't want to sort of overly criticize it. They just added lots and lots of high pressure configs to stabilize. And it worked. It cost them a huge amount of effort. And so much so that they didn't release the data because it's deemed so valuable. I prefer to solve the closed approach problem analytically because I think it is an analytic failure of the model. And so I use those explosions as diagnostic. The problem with active learning is that you lose your diagnostic. If for another diagnostic that we always use is interaction of two atoms, just the dimer curve. Now you go to any, and I talk to any computer scientist here, and I show them the atrocious dimer curve of the equivariant transformer model, which kind of looks like this if you train it on Materials project data. And they say, well, you didn't tell me that you want the dimer curve, so let's just put it in. There's only 10,000 dimer curves in the periodic table. Problem solved. Well, yeah, but actually, I was lying. I didn't need the dimer curves. I want a good model for catalysis. Dimer curves and terrible dimer curves was sort of a signal for bad extrapolation. And if you put it in, you can't test it. So it's a dimer curve as a test is good if your approach is to do something else that tries to fix the problem in general, and then you test on the dimer curves. And you can see if you've made a difference. Just similarly to what I showed you with the arsenic. That we could have just put in all those high pressure configurations, but then you go to the next material and you get the same problem because those new configurations are not in there. The way that we solved it, pair repulsion at very close range, fitting atomization energy, layer norm, that solves almost all the high pressure problems for any material, right? So that, and you use the actual data as signal.
Thank you. Maybe a short question from Mikhail Rudenko. So what is the reference of data in MLPG that you showed? What is the reference level field?
Every test has a different reference. So, and that is important, right? Because some people will say a potential, I want to know how my potential approach is, it's crummy PB data training source. Another person says, I don't care about PB, I want to know how it goes to experiment. Organic liquids have experimental densities as reference data. Some other people will say, I want couple cluster accuracy. So each test has a different target, and this is what we're working on in the user interface, how the user can, first of all, know what's the reference, be alerted to mismatches between potential data source, training data level, and test data reference, and how do you integrate the two? You should be able to go in as a user and say, click a button and say, I want everything to be experimental reference, or as close to high-level electron structure as possible. Or I want everything to be reference to the model electron structure reference, because you ask and answer a different question when you do that.
Thank you. Aslan, maybe last question.
Just asking maybe in the same direction as Alexander started earlier. What is, in your opinion, the closest analog for the coupled cluster gold standard for the bulk materials, and shall we probably start looking for a solution inside the positivity methods like RPA or GW or something like this?
Yeah, I mean, RPA again is if you look at the cases where there is some experimental data on molecule surface molecule material binding energies, RPA is better than DFT, but there are some things it gets really wrong. This is, I think, a very much an open question. There's quantum Monte Carlo, diffusion Monte Carlo, which in many cases is very accurate, but again, there are lingering questions on fixed node approximations and so on. There are people who do couple cluster for materials. And again, how applicable they are, they haven't been scrutinized to the extent that they need to be, because the demand, these are very niche fields. They used to be niche fields. I think now, with this enormous demand that the ML potentials create, now it's worth knowing and worth surveying how these extremely expensive electronic structure methods behave on a variety of systems, not just on something super specific that each researcher is talking about. So I think there will be a big rebalancing on what is worth doing and what is worth benchmarking. So I think that's the next, apart from the amount of data, that's the next big frontier.
Okay.
Josh. So I'm sorry, this is a political question. So you're now the director of the MPI in Mainz.
Yeah.
I think a lot of us have been through the MPI or through the university department in Mainz. During the time of the two Kurts, Kurt Bender and Kurt Kramer, this was kind of like Intel and AMD or Volkswagen and or BMW and Mercedes. These were rivals but also connected, and they helped to make Mainz very central. So how do you expect to be able to find an opposite number for yourself in the Mainz University as it's evolving?
I mean, I'm still exploring. I've met a couple of people. Currently, I'm also a bit new to the siloing of the German system. So the chemistry department thinks that I should be an honorary professor of chemistry. The physics department thinks that I should be an honorary professor of physics, but I can't be both. Because they don't allow it. Because it's the German university.
It would be allowed in Berlin.
And well, yeah, maybe that's a good threat. But even worse, I mean, this is the political question of the large scale, but there are very day-to-day practical questions. Like I've just discovered that if I want to enroll a PhD student who is going to work in my institute in the MPI, and they're going to get a degree from Mainz University, then their master's degree needs to match the department into which they enroll. I can't take a brilliant chemist from a top US university and walk them into the physics department of Mainz and say, please give them a PhD.
That's why I'm asking.
So,
you need to find someone, the equivalent.
So at the moment, I'm at the...
Bender, because Kurt could bend the rules. He could say, well...
Bender, I don't know. I'm not yet, I'm at the moment, I'm at the state of bewilderment at the moment, and eventually, ask me in a year, and maybe I'll have some answers.
I mean, being somewhat familiar with the German system, right? I think, for example, the computer science department of TU Berlin has a big heart. So, of course, people who are not coming with a PhD with a master in mathematics or computer science or physics or chemistry, but for example, in cognitive science, they can still get a PhD in computer science, but they will have to do one additional exam.
Yeah, sure.
And so people are very pragmatic of this. So there are very pragmatic places in the German university system.
Yeah, I need to find them. That's what I'm saying. At the moment, I'm in the state of bewilderment.
Maybe not in Mainz, but...
Okay. Let's keep some further discussion for the break also. And thank the speaker again.